Okay, so we know that there are two types of cells, electrolytic cells and electrochemical cells. So let us just learn electrolytic cell first. There are two types of electrolytes which we are going to use in your syllabus. There are two different types of electrolytes. The first is fused or molten NaCl. Fused or molten mass of NaCl means the thick paste of NaCl. The first point to explain this cell is the principle, as it says that this cell converts electrical energy into chemical energy. It's a simple principle of this cell. This basically is the definition of electrolytic cell. So that is the principle. I'll repeat. It converts electrical energy into chemical energy. The second point is the diagram. As you all can clearly see, it contains a glass beaker containing fused or molten mass of NaCl, that is the thick paste of NaCl, in which two electrodes of graphite are immersed. These two electrodes are generally made up of graphite. I have written that in the note here because graphite is a very good conductor of electricity, and these electrodes are inert. That means they don't take part in the chemical reactions. And we know that each carbon in graphite is sp2 hybridized, and that is why it will have pi electrons, and these pi electrons, they keep on moving. That makes graphite a very good conductor of electricity. So again, this electrolytic cell is made up of two graphite electrodes dipped in fused or molten mass of NaCl. To the left, I have drawn anode, which is connected to the positive pole of the battery. To the right, I have drawn cathode, which is connected to the negative pole of the battery. And that is why anode is positively charged, whereas cathode is negatively charged. The electrons will always flow from higher potential to the lower potential. That is why electrons will enter from the battery to the cathode, and because the cathode is dipped in the solution, the electrons will enter from cathode to the solution. Then through the solution, electrons will travel from cathode to anode, and then again anode to battery. This is the flow of electrons. As the electrons enter in the solution, the reactions will start. And the reaction which takes place in an electrolytic cell, it is called as electrolysis. And electrolysis actually is made up of three steps, three reactions. Electrolysis actually, it is made up of three different reactions. The moment these electrons will enter into the solution, this solution will undergo dissociation. Like NaCl will dissociate as Na plus and Cl minus. The second step is migration. Cations will start migrating towards cathode. Anions will start migrating towards anode. Remember, this is irrespective of the type of the cell. Cations always migrate towards cathode, and anion always migrate towards anode. The second step is migration, and then third step is redox reaction. So the preliminary step is dissociation. The moment the current enters the solution, the first reaction that takes place is dissociation, followed by migration, followed by redox. All these three steps, that is dissociation, migration and redox, together is called as electrolysis. So that is all about the diagram, and we'll actually see the working. As I've just now mentioned the reactions, we'll see the reactions one by one. So the third point here, in the working, we are going to learn the reactions in this particular cell. The first step, as I clearly said, NaCl, which is fused, that is a thick paste, undergoes dissociation into cations and anions. like Na plus and Cl minus. The second step is migration. Now, what is the reaction that is going to take place at cathode? As I clearly said, cations will always migrate towards cathode. So this is a cation, Na plus, we know that it is a cation. It will migrate towards cathode and it will undergo reduction. We know that at cathode always reduction takes place. So Na plus changes into a neutral atom, sodium solid. This Na plus is aqueous. And we all know that this is reduction, right? This is plus 1 to 0. The number here at the top is changing from plus means plus 1 to 0. And that means the number is decreasing, the oxidation number is decreasing. That is why this is reduction half reaction. And in reduction, reduction means gain of electron. The reaction is perfectly balanced. This is what we have seen in 11th standard. The third point here, reaction at anode. At anode, anions migrate. So which anion do we have? We have Cl minus. It will go to the anode and Cl minus aqueous, and it will also get chargeless. But we know chlorine is diatomic, so we have to write it as Cl2 gas. To balance it, this will be 2Cl minus. This clearly is oxidation. Oxidation is loss of electron. Should be written here and balanced like this. So this is 2 moles of electrons. So I will repeat, the first step is NaCl undergoing dissociation as Na plus aqueous and Cl minus aqueous. Na plus being cation will migrate towards the cathode and will undergo reduction, giving us Na solid. Cl minus being an anion migrate towards anode and undergoes oxidation, giving us Cl2 gas. So these are the 2 observations. At cathode, sodium solid is getting deposited literally here. In the diagram you can show that here. This is the cathode. So at cathode, sodium solid is getting deposited here layer after layer. And then this rod will get swollen up and sodium literally will get deposited here. Whereas this rod will turn greenish because here we are going to get chlorine and we'll have bubbles of chlorine like this here. This is the actual visible confirmation that the reactions are taking place. And obviously these reactions are non-spontaneous, as I've already explained. All these reactions are happening only because we are supplying electricity. The moment you stop the supply, these reactions will stop. These reactions are not taking place on their own. We are carrying it out. So these are the reactions, as you all can see. And then I'm going to write the net cell reaction. This is just a theoretical point. We are literally going to add these 2 reactions. The net cell reaction or the overall cell reaction. I can add oxidation half reaction and reduction half reaction only when the coefficient of electron is same. Here, in this case, the coefficient of electron is not same. As you all can see, this is 1 mole of electron, whereas this is 2 moles of electrons. So I need to make it same just by multiplying this reaction by 2. So this will become 2 moles of Na plus, 2 moles of electrons and 2 moles of neutral sodium atom. Now I can add this, and after adding, the 2 moles of electrons and 2 moles of electrons will get cancelled, and what I am left with is 2 Na plus aqueous. Here this will get 2 Na plus, then the other reactant is 2 Cl minus aqueous. This is going to give me, this will be 2 Na solid plus Cl2 gas. So these are the reactions. You can clearly see NaCl undergoing dissociation as Na plus and Cl minus, and then at cathode, Na plus by gaining electron is undergoing reduction and sodium solid is getting deposited, whereas at anode, Cl minus aqueous is losing electron and Cl2 gas is liberated at anode due to oxidation, and this is the net cell reaction. Now the other electrolytic cell, the other example in your syllabus is that of NaCl only, but it is the aqueous NaCl. Here we have taken the thick paste, fused or molten mass of NaCl. This is a thick paste of NaCl. Now I'm going to change the electrolyte where the solute and solvent is same. Here the solute is NaCl and the solvent is water. The next example, solute is sodium chloride and solvent is water. Then what is the difference? The difference is in the proportion in which NaCl and water are mixed. Here, we have taken a lot of quantity of NaCl and a thick paste and just little bit of water. Now, I am going to change the proportion. I will be taking a lot of water and little NaCl. That is why the electrolyte is NaCl aqueous. Why this example is included in our syllabus? Just to make it understand that just by changing the proportion, the substances which get deposited or liberated, that is which gets reduced or oxidized, can be different. How that happens, let us just learn. So I am going to explain the electrolytic cell containing NaCl aqueous. Let us see directly the reactions because the principle and the diagram is exactly the same. So now I am going to take an electrolytic cell containing NaCl aqueous. Here also the first step is dissociation. NaCl aqueous, lots of water, little NaCl, undergoes dissociation as Na plus and Cl minus. Here dissociation takes place. There dissociations, that is the first difference. Like here we have a lot of water, so the ionization of water cannot be neglected. That is why water will also split up, giving its cation as H plus and OH minus. This is the basic difference. Here water is negligible. It is just present in a little quantity, like moisture. So that is why the ionization of water is not considered here. But here the ionization of water cannot be neglected. This is the first difference. Now secondly, we have to see the reaction at cathode. Now here, as I have written only one cation, right? Because there is no other cation which is having competition with Na plus. Yes, literally, it is the competition which Na plus is going to face here. Here the Na plus of NaCl migrates towards the cathode and by gaining electron, 1 mole of electron is going to get converted into sodium solid. But this Na plus is going to be challenged by the H plus of water. Even H plus is going to migrate towards cathode and you are going to have reduction reaction. Now I would have written H plus reduction, but as per the textbook I am writing the reaction. There in the textbook they are writing the reaction of reduction of water. And this is by gaining electron is going to give you H2 gas and OH minus aqueous. Now from where these products come, there is a trick to remember, there is a mechanism to this. When in person I will take the lectures in the classroom, I shall explain this. But this is as per the textbook, that water undergoes reduction and gives H2 gas and OH minus. I need to balance this reaction. In order to balance this reaction, this should be 2 times. So this will be 2 times. And here we'll have 2 moles of electrons. You can clearly see the reaction is balanced. Let us check whether the reaction is balanced or not. Here we have 4 hydrogens, like 2H2. Here we have 2 hydrogens here and 2 here. The reaction contains 4 hydrogens on both the sides. 2 oxygens and 2 oxygens. Even the charge is balanced. You can see -2 here and -2 here. So that is the reaction which takes place. One more data I am going to write here. This is an important data. I will explain it. It is E naught RED. How do we read this? This 0 in this chapter, you should read it as standard. This is standard, this is reduction, and E, you should read it as potential. So together, this is standard, reduction, potential. The standard reduction potential of sodium, it has a value equal to minus 2.71 volts. This is a value. I'll explain what does that mean. Whereas the standard reduction potential of water, this is minus 0.83 volts. Negative of 0.83 volts. So these are the reduction reactions. As you all can see, Na plus being a cation goes to cathode, gains 1 mole of electron and gives sodium solid. This is a standard reduction potential of sodium. Then ideally speaking, we should be writing H plus, because H plus of water, it is a cation. It migrates toward cathodes and should give you H2. But in the textbook, they have shown you the reduction of water. So water, by gaining 2 moles of electrons, undergoes reduction and gives hydrogen gas and OH minus ions. Now, I'm not saying that these two products is what we are getting. Out of these two, only one product is what you are going to get. Now, which is that product that we are going to get? I'll explain. First, let me complete the reactions at anode. At anode, we know which ions migrate. It is the anions. So here we have Cl minus. First thing first, let us see at anode. Cl minus gives Cl2 gas and 2 moles of electrons. This is a reaction. Now here, ideally speaking, I should be writing OH minus here. But again, as per the textbook, I am writing the reaction, that is the oxidation of water. Water is going to undergo oxidation. Oxidation is loss of electron. So what we are going to get is O2 gas and H plus and electrons. I need to balance this again. This should be 2, this should be 4 here, and there should be 4 moles of electrons. Again, semicolon. Now this time it is standard oxidation potential, E0 OXI is standard oxidation potential. That of chlorine, the value is minus 1.36 volts. Here the standard oxidation potential, of water, it is minus 0.4 volts. Now let's get back here. The question is, what are we going to get at cathode? We're going to get sodium solid or H2 gas. These are the possibilities. We are not saying that we are going to get both these products. These are the possibilities. Out of this, only one will be the product. Which is that? So literally, here we are having competition between Na plus and H plus. Who's going to win the competition? As you all can see, out of these two numbers, that is minus 2.71 and minus 0.83, this is a bigger number. That means the standard reduction potential of water is more than that of sodium. The standard reduction potential of water is minus 0.83, which is greater than the standard reduction potential of sodium, which is minus 2.71. Hence, water wins the competition and hydrogen gas will be liberated at cathode. I'll repeat. The standard reduction potential of water is more. You know that दो negative number में जो दिखता छोटा है वो होता बड़ा है, तो ये number बड़ा है. So the standard reduction potential of water is more than that of sodium. Hence water wins the competition and hydrogen gas will be liberated at cathode. Here at anode, who's going to win the competition? Cl minus is migrating towards anode, Cl minus of NaCl, and having competition with OH minus. Here, the standard oxidation potential of water is more than that of chlorine. Hence, it is expected that water should win the competition and oxygen should be liberated at anode. But instead oxygen, chlorine is liberated. Chlorine is observed practically. Oxygen does not get liberated. It is expected theoretically as per the values. But instead of oxygen, what we get is chlorine. This happens due to over voltage phenomena. I'll repeat here. The standard oxidation potential of water is more than that of chlorine. Hence, it is expected that water should win the competition and oxygen should be liberated at anode. but instead of oxygen, what is observed practically is chlorine. This happens due to over voltage phenomena. Let me repeat, this happens due to over voltage phenomena. Now what is over voltage phenomena? See, these values, these are theoretical values. What theory says is minus 0.4 volts is sufficient enough for the OH minus ions to migrate towards the anode and get discharged. See, as you all can see, this is negative voltage. That means we are supplying the voltage. You know, these are non-spontaneous reactions. We are studying electrolytic cell. In electrolytic cell, we have already seen in the last lecture that the reactions are non-spontaneous. Non-spontaneous means these reactions are not taking place on their own. We are doing it. In the beginning of the lecture also I said, because we are supplying, this dissociation takes place, even the migration takes place because we are supplying electricity. So we are literally pushing these anions and cations towards their respective electrodes. So this minus 0.4 volt means we are supplying this much volt. Theory says that 0.4 volt is sufficient enough for us to force OH minus to go towards anode. We are pushing OH minus, and minus 1.36 volts is sufficient enough to push Cl minus towards the anode. But practically this voltage is not sufficient enough. Practically the voltage required to push OH minus towards the anode is much more than 1.36. This is over voltage phenomenon. There is a discrepancy between theory and the practical. So theory says that minus 0.4 volt, that means the supplied voltage is sufficient enough for us to push OH minus towards the anode, but practically it is not so, and that is explained in one word, that is over voltage phenomenon. So I'll repeat, since the standard oxidation potential of water is more than that of chlorine, it is expected that water should win the competition and oxygen should be liberated at anode, but instead of oxygen, chlorine is observed. This happens due to over voltage phenomenon. So here we have this as a winner. That is what we feel, but it is not. The actual winner is Cl2. We feel that this should be the winner, correct, as per the theory. But what is actually happening is that chlorine is winning. So you see, these two are the winners. At cathode, what we are getting is hydrogen gas. At anode, what we are getting is Cl2 gas. So if you compare these two reactions, this is NaCl fused mass, you can see the difference. Here at cathode what we are getting is sodium. But just by changing the proportion, instead of sodium now what we are getting is hydrogen gas. At anode the product is same, Cl2 gas, but the difference is here. And then we can write the net reaction obviously, that is by adding these two reactions. The last step, which I am obviously not going to write, it's very simple. You can add these two steps. 2 moles of electrons and 2 moles of electrons will get cancelled, and whatever is left you can write the net cell reaction.